Good morning, friends. Today we are going to discuss scalar and scalar fields. Scalar is usually said to be a physical quantity that only has magnitude and no other characteristics. That means basically scalar is a physical quantity. Unless and until something is a physical quantity, you cannot distinguish whether it is a scalar or a vector or a tensor. First of all, it must be a physical quantity. That means physical quantities can be characterized as a scalar when it has only quantity is enough to explain it, a particular physical unit or quantity, and no other characteristic is required to explain it. Say, for example, the distance between two bodies is a scalar. That means from this boy to this boy, if you measure this length, and from this boy to this boy, it is 50 meters only. The value never change when you are measuring from here to here or here to here. So this length 50 meters is called the distance. So distance is a physical quantity because it is not depending on the direction or anything else. Just this quantity is enough to explain the distance between these two persons. Then the distance is a physical quantity which can be considered as a scalar. Okay, so some other examples for the scalar. Electric potential at a point inside the medium is also scalar, and charge, which is a fundamental entity, is again a scalar. So charge never need a direction or anything else to describe charge. So how much quantity of charge is there? That is the basic question. So charge again a scalar, and of course mass is also scalar. Another important thing is one more example. I mean to say volume. Volume is again a scalar. Why it is so? Volume, I can say, inside this cube or sphere or rectangular prism or circular cylinder or a square pyramid or a cone, whatever it may be, to better understand what is exactly volume is, inside this shape, how much space is available inside this space, this particular shape, whether it is this shape or this shape. Inside this shape, how much space is available, or otherwise, in differently we can say that how much space it is occupying, how much space this shape is occupying. So that can be called the volume. Again, volume, the units are for the volume either liters or cubic meters or cubic centimeters for that matter. I can say like this: how many liters of milk you can pour in this shape? How many liters of milk you can pour in this shape? Like all the shapes. Once maybe the shape is changing, but the amount of this one, based on this, if you tilt it this way or this way, whatever direction you want to, but the space or the amount of space inside this, or otherwise how much amount quantity of milk you can store in this particular shape will not change. Whether this cylinder is upright or whether cylinder is tilted 90 degrees, the amount of milk we are storing is same. That means volume is not depending on the direction. So obviously we can say volume is a scalar. Time, of course, time won't require any direction or any other physical things to explain the time. Just the quantity, how much time we are spending. Of course we can't bring back the time we are spending. So time is most precious thing, of course, everybody knows that. Time again a scalar quantity. The speed, what exactly speed is? Speed means, generally, in normal terms, I am going to explain what is speed. In general terms, how much distance we are traveling in a particular time. Say for example, if we are walking, maybe we can move, or we can walk, or we can sweep probably around 3 kilometers in 1 hour. If we are running, maybe we may run 7 kilometers. If a car is moving, if a car is running with high speed, it may take in just 1 hour it may go 60 kilometers distance. So at a particular time interval, how much distance we are traveling or an object is traveling is called speed. Here I am talking about the distance, but the distance not necessarily place the object at a particular another place. Say for example, let me explain in this way what exactly speed is. See, there is a boy who is at 3 km per hour speed. He is moving like this. After 1 hour, he come back to the place where he started. There is another boy who started moving from this place to this place. After 1 hour, he reached from point A to point B. That means, or otherwise, this is not the boy. Let us say a boy is running around the circle. A small ant is started moving from this place to this place. Or ant or a tortoise, say for example, let me say it is tortoise. A tortoise or a turtle, tortoise start moving from A to B. A tortoise is able to change its place from A to B, whereas a boy who can run faster than this tortoise, of course, never go away. He started at point O and ended his journey at the same point O. That means displacement or a distance, all these things are different. Like speed, the definition of the speed is rate of change of distance. So here the speed is a scalar. Okay, once we discuss about the velocity, we can better understand what exactly speed is. Okay, coming to the some most important aspects or more highly technical aspects. Of course, we already have the basic idea about up to this what is speed, or whether speed is a scalar or vector, and all the things we already studied up to our plus 2. Now, at the degree level, graduation level, let us deeply understand what is scalar exactly. Formally speaking, a scalar is unchanged by a coordinate system transformations. We know that in first year intermediate, we discussed, we in mathematics we studied coordinate system transformations. So when the coordinate system is transforming, whether it is translatory or rotatory transformation, a scalar quantity will not change. Yes, it is. Say for example, whether your coordinate system is this blue color xyz, you are measuring an object weight or mass 1 kg. If your coordinate system is tilted, even after your coordinate system is tilting, your object weight is 1 kg or object mass is 1 kg only. So, scalars will not change when the coordinate systems are transforming. Whether the coordinate system is transforming rotatory or even in translatory also, it will not change. Another important point is, in classical theories like Newtonian mechanics, rotations or reflections preserve the scalars unchanged. That means mass and other things will not change in Newtonian mechanics according to the classical theories. So scalars will not change. So this is another point we should remember that. Coming to the relativistic theories, Lorentz transformations or the space-time translations, they are also preserving the scalars. In the last chapter of this semester, we are going to study relativistic theories and Lorentz transformations elaborately. Meanwhile, I would like to give you a small exercise to you people. Just prepare a small notes on theory of relativity. Small notes, or otherwise take the help of YouTube. Just see the videos and write your own words. In your own words, what is relativity? That's enough. If possible, some of you may write a small notes on Lorentz transformations. Of course, at the last chapter, we have exclusively studying about relativistic theories and Lorentz transformations. So, until then, you just remember that even in the relativistic theories also, scalars will not change. In classical theories like Newtonian mechanics and Lorentz transformations also, this will not change. So, the quantity doesn't depend on the length of the base of the vectors of the coordinate system. Say for example, in coordinate system, whether your coordinates are say for example length coordinates, if whether they are the bases are in, you are measuring in centimeters or meters, whatever it may be, based on the base of the vector your coordinate system, the entire quantity of the scalar will not change. Okay, so that is another important point. Say for example, let us take the volume. We already discussed that volume is a scalar. Let us say we are measuring the Cartesian coordinate system volume. If you measure the volume of a cube, even in cylindrical coordinate or in spherical coordinate, whatever coordinate system you are using to measure the volume of a cube, the volume will not change, but just the formula to compute the volume of the cube will change according to the coordinate system you are using. That means any changes in the coordinate system may affect the formula for computing the scalar, but not the scalar itself. Okay, that is important thing one should remember. Okay, relativistic scalars. Relativistic scalars means the theory of relativity come into picture when the objects are moving at the speed comparable to the light speed. We all know that the light is traveling at a tremendous speed, that is, in a single second it travels 3 lakh kilometers. 3 lakh kilometers it travels. Such a tremendous speed. If an object is moving at least at 1 lakh kilometers per second or 2 lakh kilometers per second, then the normal Newtonian mechanics will not explain, is not sufficient to explain all physical phenomena. Then Einstein's theory of relativity will explain us all physical laws at such a high speeds. So the scalars, how the scalar quantities at such a high speeds, so they are, we can simply say it as relativistic scalars. In classical physics, that means non-relativistic. What is non-relativistic? Means the speeds of the objects or the coordinate system is comparatively very less with the speed of the light. So in that case, many of the scalars need to be combined with the quantities that are treated as the 4 vectors when you are discussing same things at high speeds, relativistic scalars, high speeds. Let us consider the examples. What are the examples? Say for example, charge density at a particular point in a medium. We already know that it is a scalar in classical physics, but in relativistic, that means when you want to measure the charge density at high speeds, you have to consider the 4 vector tensor. Of course, they are scalars only, but not one thing is enough. 3 vector is not enough. That means density means x, y, z is not enough. The 4th coordinate, time coordinate will also, this x, y, z is not sufficient to explain the charge density at high speeds. You need to have a 4th coordinate, that is time coordinate, ICT, time coordinate. So that's it. Energy density must be combined with the momentum density, pressure into stress and energy tensor. So this is the way the scalars are changing at relativistic mechanics. Okay, let us discuss about what is scalar field. this is about scalars, and now we are going to understand scalar field. A function of a space whose value at each point is a scalar quantity. You are seeing a beautiful picture on the screen. See here in this picture, each point is a scalar. Each point is a scalar. So this a function which can describe this shape, this is called the scalar field. Okay, so that means scalar means a physical quantity which don't have direction or any other things except the quantity to explain it. Okay, scalar fields are required to be independent of the choice of the reference frame. Scalar fields are required to be independent of the choice of the reference frame. Whether you are measuring a particular scalar field at point B by an observer A, here the observer A is traveling, whereas the observer C is stationary. Scalar field at B, both are measuring the same. Scalar fields are required to be independent. It will not change whether a coordinate system fixed to A point Mr. A, Miss A, which is relatively moving, Mr. C, who is at stationary. Both are measuring same quantity. What is exact meaning of that? Any two observers using the same units. Here this condition is most important. Same units. Both A and C should use same units. We'll agree on the value of the scalar field at the same absolute point in space, regardless of their respective points of origin, whether Mr. C is here or Miss A is here, wherever their points of origins are there. But the scalar field they are measuring on B is same. So now we are going to discuss some examples for the scalar fields. Temperature distribution throughout the space is a scalar field. Here this diagram is actually giving you the thematic or temperature distribution over a plate. Plate is at the x-axis. Heat is giving from heat this way. So this is more red means more heat, blue color means coldness, absence of heat. Of course, coldness is nothing but absence of heat only. Okay, so temperature distribution throughout the space is a scalar field. That is the point you should remember that. And the pressure distribution in a fluid, again a scalar field. Please don't misunderstood that. Please don't think that these arrows are showing some direction. No, not at all. As the depth is increasing, here you can understand that here the surface, this is the water or the liquid, whatever it may be. As the depth is increasing, we know that pressure is equal to density rho of the liquid, and g is the gravity acceleration due to gravity, and h is the depth. As depth is increasing, the pressure is increasing. So to show that the pressure is increasing, these arrows are shown. Please don't think that these arrows are actually giving you some direction. No, not at all. Not at all. Not at all. Pressure distribution in a fluid is a scalar field. Okay, and spin zero quantum fields. Quantum fields, or otherwise, let me say in this way: quantum fields whose spin is zero. Quantum fields whose spin is zero, also scalar fields. If a spin is not zero, whether it is half integral or any other integral, let us say spin is 1, 2, 3 h cuts, we are not talking about them, or half 1 by 2 h cut, 3 by 2, 5 by 2, whatever it may be, we are not talking about them. The quantum fields whose spin is zero, they are also scalar fields. Example is Higgs field. We know that Higgs boson is considered as the God particle. This is again a small assignment I would like to give you. What is Higgs boson? Higgs boson. What is Higgs boson? And what is Higgs field? Please make a small notes on that. And next class we are going to check it. Please remember that these things will not cover under any university formal syllabus, but as a physics students, everybody is expected to know or have an idea about Big Bang theory, Higgs particle or God particle. These are all expected to know by any science graduate, especially those who are studying physics as their subject. So don't think that, say, oh, sir, this is not in the syllabus, I don't want to do it. No, you are a student of physics, you are supposed to know it. Okay, so take this as an opportunity to learn. If you find any difficulty in understanding Higgs boson or Higgs field concepts, well, tomorrow we will discuss separately in doubt clarifying session. Okay, let us move on to next one. A scalar field is a tensor field of order 0. These tensors we are going to study. These tensors we are going to study in a separate chapter, that is rigid body dynamics, in this semester itself. So let me tell you one thing. Once we go to that chapter, probably that is fourth chapter, in that chapter, rigid body dynamics chapter, I will say that in this world there is no scalar, no vector at all. All the physical entities, all the physical quantities are just the tensors of different orders. If the tensor of order 0, we call them as the scalars. Tensor of order 0, we call them as scalars. Tensor of order 1 is called vectors. Tensor of order 1. Order 1 tensors are vectors. Zeroth order tensors are the scalars. So scalar field is nothing but a tensor field, but this tensor field order is 0. Okay, hope you understand it. If you don't understand, just make me remember about this. We will elaborately discuss once we study the rigid body dynamics and momentum tensor and all the things. Okay. Let us move on. Scalar field be continuous, or often it may be continuously differentiable to some order, maybe first order, second order, it may be differentiable. Till that, it may be continuous. Okay. And another thing is in physics, scalar fields often describe the potential energy associated with a particular force. Scalar fields often describe the potential energy associated with a particular force. What are the example? Gravitational potential, electrical potential, temperature, humidity, or pressure field, such as those used in the meteorology. In meteorology, temperature we are using to predict weather reports, weather forecasting, temperature, humidity, pressure, all these things we are using. So these potential energies, they are associated with the a particular force, gravitational force associated with gravitational potential. Here the gravitational potential is a scalar field. Gravitational potential is a scalar field, whereas gravitational force is a vector. Gravitational force is a vector. Gravitational potential is a scalar field. Electrical potential is a scalar field, whereas electrical force is a vector again. That means why this gravitational force is a vector? Because gravitational force pull is always towards the center of the earth. Always towards the center of the earth. That means it has the direction. But the gravitational potential don't have the direction. What does it mean exactly? I will explain in this way. Say for example, from the center to point, let me like this. From center of the earth to point A, this distance is, say for example, 10,000 kilometers. That is center of the earth, not from the surface of the earth. 10,000 kilometers from center O to point A. Here also 10,000 kilometers. Or let us say not the 10,000 for easy understanding. Let me say maybe some 5,000. Let me put it in this way. This is the earth. This is the center of the earth. From this is O. From here to here 5,000 kilometers. Here to here another 5,000 kilometers. This is point A and this is point B. See, remember this. Here the gravitational force is in this direction. Any object from point B is moving this direction. Any object from point A move in this direction. But the gravitational pull is here. The pull is exactly equal to here. That means the potential is exactly equal. That means this potential don't have the direction. gravitational potential at a particular place don't have the direction. It is the gravitational force which have the direction. Similarly, electrical potential don't have the direction. It is associated with the vector electrical force. Okay, so this is what I would like to give you details. Okay, in quantum field theory, scalar field is associated with spin zero particles. Spin zero particles. It is associated with the scalar field is associated with the spin zero particles. The scalar field may be real or it may be complex valued. Scalar field not necessarily real entity all the time. It can be a complex value, complex entity. That means A plus IB form. We already studied complex numbers, right? Why we are studying complex numbers in mathematics is just to understand the physics. This quantum field theory and all these things. That is the reason why we are studying complex numbers there. Okay. Complex scalar fields represent charged particles. This is the most important. Once you those who aim to study higher studies in physics, so these points are very important. Please note it down. Complex scalar fields, they are representing the charged particles in the universe. Charged Higgs and charged pions, and these are all the things. Okay, you are going to study in detail in your final year, that is modern physics. Particle physics is a separate branch of physics. There you will study a large hadron collider, LHC, in Switzerland, Swiss border. The entire scientific community is working very hard, spending billions of rupees to understand the origin of the universe. So how we can understand? By studying these Higgs and pions and all these things. Okay, so very important points. Of course, as I told you earlier, all these things are not covered in your general syllabus. Okay, so please don't neglect these things just because you don't be asked in your university exams. The first 10 slides are enough for you to write and get the O grade, outstanding grade in your university exams. But these things are very important for you, my dear students, as per the physics is concerned. Okay, let us move on. The role of scalar fields playing a vital role in studying the origin of the universe, in explaining the origin of the universe. Okay, scalar fields are hypothesized to have caused the high accelerated expansion of the early universe. So we know that once the Big Bang happened, the universe started expanding. So inflation. So that is inflation. Okay. Scalar fields helped to solve the horizon problem and giving a hypothetical reason for the non-vanishing cosmological constant of cosmology. See, this is the horizon problem. We see what the Big Bang theory says is earlier the entire universe is around the football size. It got expanded and expanding, continuously expanding. What does it mean? Maybe it is expanding billions of kilometers, but this edge is there, no? At this edge, beyond this edge, nothing else should be there, because according to Big Bang theory itself, according to Big Bang theory itself, there is nothing in this universe before Big Bang except in this small football size. Beyond this football size, there is nothing. Everything is concentrated in this football size. It is get expanding and expanding and expanding. Say for example, by today it get expanded up to this point. What does it mean? There is nothing beyond this point. There is nothing beyond this point. But that is not true. That is not true. That is called horizon problem. This beyond this horizon, to explain this beyond this horizon, cosmological constant you need to understand. This non-vanishing things and all these things can be explained by using the scalar fields only. So such a high important value these scalar fields are playing, vital role they are playing in explaining the universe origin and everything. So another third assignment to you, my dear students. This assignment is exclusively for those who are interested in the cosmology. Okay, so come with a small notes on horizon problem and cosmological constant. Horizon problem and cosmological constant. Separately we will discuss, not in the general class. Separately we will discuss about this. Those who have more interest. Why I don't want to give to the entire class, especially these two, is I require some zeal in understanding it. It doesn't mean that I am not giving to anyone else. I am giving to all of you. This is an open offer. Those who are interested, if the entire class is interested in writing or studying these two things, I am the most happiest person. Okay, let us move on. Massless scalar fields are known as the inflatons. Massless scalar fields are known as the inflatons. Massive scalar fields are Higgs-like fields. They are creating the Higgs-like fields. So this is what. Okay, my dear friends, those who have any doubts, you please drop your doubts in the questionnaire box, or you can mail me at any time. So this is all for today.